When Hubble captured 3I/ATLAS after perihelion, the moment that shatters most comets, scientists expected cracks, chaos, complete destruction. Instead, the images showed something that defied physics, a sharp, stable core with zero fractures, no breakup, no disorder. Then, enhanced processing revealed hidden jets and a massive 37,300-mile anti-tail that shouldn't exist. What stunned scientists most? This isn't random comet behavior. It's organized, controlled, predicted. Let's dive right in. To understand why scientists are genuinely stunned by what Hubble captured, we need to talk about what perihelion actually does to comets. This isn't just getting close to the sun, it's entering a zone where most objects simply don't survive intact. As a comet approaches perihelion, solar radiation intensifies rapidly. Within hours, surface temperatures spike from deep freeze to levels the object was never built to handle. Frozen water and volatile gases don't gradually melt. They explode directly from solid to gas through sublimation. But here's what makes it lethal. This doesn't happen evenly. Some areas heat faster than others. Internal pressure builds quicker than the material can safely release it. Deep inside, invisible cracks form. As gases force their way outward, these fractures expand. Jets fire unpredictably. The comet's rotation destabilizes, and large chunks break free. We've watched this destruction countless times. Comets enter perihelion with clean shapes and exit as debris fields, stretched, split, or shattered within days. The pattern is so consistent that astronomers treat post-perihelion images as the ultimate stress test, expecting disorder, asymmetry, and clear structural failure. So, when Hubble pointed at 3I/ATLAS on November 30th, 2025, 1 month after it passed through this cosmic furnace, scientists knew exactly what to look for. Cracks should warp the nucleus. Uneven jets should distort the gas cloud. The structure should look damaged and unstable. Except this time, none of that appeared. The image that came back stopped researchers in their tracks. The nucleus appeared sharp and tightly concentrated with no stretching or deformation. When comets sustain damage, you can see it. The core looks smeared or irregular. But 3I/ATLAS showed clean lines, compact structure, zero visible fractures. The surrounding coma expanded smoothly in all directions, roughly circular and evenly distributed. There were no sharp plumes, no directional streaks from chaotic jets. In damaged comets, this cloud becomes lopsided because jets push material unevenly. Here, the expansion looked balanced, as if release was happening under controlled conditions rather than explosive chaos. What made this striking was what Hubble didn't see. Brightness remained centered and uniform with no irregular patterns exposing hidden fractures. This telescope is designed to catch these details. If damage existed, Hubble would have found it. Think about what this means. Decades of observations show how comets behave after perihelion. Warped clouds, twisted tails, brightness variations from uncontrolled outgassing. 3I/ATLAS displayed none of it. Instead of looking broken, it looked composed. And that created a puzzle, because this stability didn't mean the object was inactive. It meant whatever was happening wasn't violent enough to destroy it. Which raised the question, if it's not breaking apart, what is it doing? Hubble's focused view showed core stability, but couldn't see everything. ESA's JUICE spacecraft, observing from a different position using just its navigation camera, revealed what Hubble's narrow field missed. Two distinct tails behaving in completely different ways. The first was a plasma tail, thin, sharply defined, stretching directly away from the nucleus. This tail doesn't follow orbital paths, but solar wind direction, made of ionized gas actively stripped away by charged particles from the sun. The critical detail, plasma tails, only exist when fresh material is being released continuously, right now. They don't persist on their own. The second was a dust tail, broader and heavier, drifting at a different angle. Dust responds to sunlight through radiation pressure, not electromagnetic forces, which is why dust tails curve and lag behind. Here's why this matters. These tails only separate clearly when new material is actively being released at the moment of observation. If activity had ended near perihelion, both would blur together or fade unevenly. But both appeared simultaneously, cleanly separated, meaning one thing. 3I/ATLAS was actively working, releasing ionized gas and solid particles at the same time. That sustained, controlled release requires an internal process still operating, still managing energy. Suddenly, the contradiction made sense. Core stability doesn't equal inactivity. The inner structure remained intact, while controlled release happened at specific surface locations. What's rare is this combination in an object that just survived perihelion. Most comets releasing material this late do so chaotically. This looked organized. Two spacecraft from different angles told the same story. Hubble showed order at center. JUICE revealed precise motion beyond. Together, they painted a picture of something operating with control where only chaos should exist. But the real revelation was still buried in Hubble's data. When scientists first examined Hubble's raw image, it appeared unremarkable. Even brightness, round cloud, nothing unusual. But raw telescope data often hides the most important details. They applied enhancement filters to amplify subtle brightness variations and expose patterns connected to rotation. As soon as these activated, everything changed. The circular coma showed distortions near the core. Brightness shifted noticeably. As processing continued, clear structure emerged. Two distinct jets appeared from opposite nucleus sides, narrow, focused, aligned in stable configuration. One extended toward the sun, the other created an anti-tail in the opposite direction. Anti-tails are rare because they demand precise geometry, exact timing, and controlled release. In most comets, unstable rotation makes maintaining this impossible. Random tumbling destroys clean alignment, but 3I/ATLAS's anti-tail remained sharp, stretching 37,300 miles from the nucleus. That scale requires steady rotation and sustained directional release over time. Two opposing jets suggest fixed surface source regions rather than random explosions. The internal structure is organized enough to channel release through specific pathways instead of breaking apart under pressure. This aligned with JUICE's detection. Separate plasma and dust tails showed active release. Hubble revealed where it originated and how it was structured. What appeared stable was actually precise balance between integrity and continuous activity. For an object that just survived destruction conditions, this is profoundly unusual, and once scientists saw this structure, they realized something unsettling. They could test it against predictions made before images were taken. What truly disturbed scientists wasn't just the structure. It was that it had been predicted beforehand. Before Hubble's November 30th image, researchers built physics-based models forecasting 3I/ATLAS behavior after perihelion. These weren't guesses, but mathematical calculations assuming consistent forces. Chaotic systems are nearly impossible to predict precisely, but organized systems leave mathematical signatures. The models predicted released material wouldn't form typical trailing tails, but drift into a specific sunward region, shaped by rotation, radiation pressure, and non-gravitational forces. Calculations described expected geometry, narrow, elongated, concentrated, stretching tens of thousands of kilometers by late November. Scientists face not one mystery, but a web of observations that don't fit established categories. 3 3I/ATLAS is displaying behavior, composition, and motion, placing it between what we know and what we don't yet understand. So what are we actually looking at here? The Hubble images have completely rewritten our understanding of 3I/ATLAS. This isn't a typical comet that survived perihelion through luck. This is an object displaying organized behavior where chaos should dominate, predictable motion that was calculated before observation, and chemistry that fundamentally doesn't match what comets are supposed to be. The sharp, intact nucleus after extreme stress, the controlled dual jets forming a 37,300-mile anti-tail, the low water content paired with unusually high metallic signatures, the X-ray emissions without corresponding mass loss, the non-gravitational acceleration without debris clouds. Each data point pulls 3I/ATLAS further from the comfortable categories we've used to explain interstellar visitors. And this investigation is far from over. More Hubble observations are incoming. Ultraviolet analysis is underway. Scientists are already planning follow-up studies as this object continues through our solar system. Whatever 3I/ATLAS truly is, it clearly hasn't finished revealing its secrets. The evidence suggests we're witnessing something that challenges fundamental assumptions about objects from beyond our solar system. And as new data arrives, the picture will only become clearer or stranger. If you want to stay updated on every development with 3I/ATLAS and other space discoveries that challenge what we know, hit that like button, subscribe to Galactic Breaking News, and turn on notifications so you never miss an update. Drop your theory in the comments. What do you think 3I/ATLAS really is? We're covering this story as it unfolds, and you'll want to be here when the next revelation drops.